Hey everybody, welcome to another fantastic episode of Google Developers Live, where we here at Google get a chance to talk to you about all the amazing things going on the web and the tech and all the platforms and the fantastic things you can do with it. My name is Colt McCandless. I'm a developer advocate here on the Chrome team, and I mostly work with web performance issues as well as web gaming. Now, what I'd like to talk to you today about is something that's very near and dear and close to my heart, and that's compression. Today we're going to be talking about GZIP on the web platform and how you can modify it and address it and munge it to try to minimize your website memory footprint and actually get faster loading data. Now, before we get into this talk too much, I'd actually like to point out the perf matters hashtag. This is a fantastic hashtag that's being used all around the intertubes on various social networks for people in web performance who are trying to find the same problems and address difficult issues and have conversations about performance in interesting and insightful ways. So use this hashtag if anything during this talk is interesting or inspiring. Feel free to go to your favorite social media network of choice. It's a fantastic outlet and you need to be following it. So with that, let's get into things. So let's start at the beginning. I can't really talk about compression on the web without actually taking a look at the state of the web today. Now, besides being filled with cats, there's actually some interesting data out there for us to look at. There's a great site called httparchive.org, and what this site will do is actually run large amounts of website through processing filters during the day. So what'll happen is they'll take 300,000, 400,000 very common websites, run them through a processing system, and then scrape information about them to present on their page. Now, what you can see here in this graph is actually one of the latest studies that shows the average bytes of a page per content type. So what this graph shows us is that images for an average site actually take up the lion's share of the content that's being streamed to users. In fact, it's more than 50%. It's actually a massive amount of the content being delivered, while scripts actually remain the second largest, ending up at around 260K or so. Now, the interesting thing about this is when you look at the individual response sizes, you see a similar trend. Of course, Flash being one of the largest sizes per number of responses, but of course that comes down to the fact that you generally only have one or two flashes per page where they tend to be pretty large. Whereas JavaScript or PNGs or JPEGs tend to be lots of requests for a page, and that actually drives that number down. So what we're looking at here is basically a vision of the web that shows that we're dominated by images and we're dominated by image data. But I'm not necessarily sure that means that we can give up on trying to minimize and reduce the size of the text data that actually drives our web. So let's take a look at this. This is another great set of charts from HTTP Archive. And effectively what you're looking at here is three graphs showing the transfer size against the number of requests, right? And so what you're seeing is over time, our number of requests have remained pretty constant over the past couple of years, while you see a general increasing trend in the overall size per request. Now, this is specifically three graphs for HTML, JavaScript, and CSS. What this is telling us is that while images make up the lion's share of the internet right now, text information, the backbone of these three formats, isn't going away anytime soon, nor is it slated to get any smaller. So for most people, they would say, well, if the web is mostly images, why should we care about text? Well, here's why. You see, images may be fantastic and they may be the dominant form of content for us, but it's apparent and been shown that they're not as small as they could be. So for example, let's take this fantastic image, which was captured on a camera. This is about 1 megapixel of data. Now, if we save this as a PNG file, it actually comes out about 2.3 megabytes of data. Now, for those of you playing the home game, you'll note that HTTP Archive averages that the average website out there is about 1.2 to 1.1 megs of data. So this single PNG image, if hosted on your website, is already larger than the average size of a website on the internet. Now, PNG is fantastic. It allows you to get transparency, and it does support GZIP compression internally as a format, but it really only supports a lossless encoding, which means you're not really getting rid of any visual data that may be redundant. JPEG, on the other hand, as a format, is built both a lossy and lossless encoder. This allows the JPEG encoding system to actually remove visually redundant information from the image so that you don't really notice it's gone, right? The human eye is pretty complex, but still at 32 bits per pixel, there's a lot of information that we can't discern. So if you JPEG this image, you lose the ability to get transparency. However, you do cut the size of the image down to 297K. Now, these have been the two mostly dominant image formats, besides animated cat GIFs on the internet. But earlier this year, internet technology evangelists and other enthusiasts decided that, maybe we weren't done here yet. Maybe the compression system of JPEG wasn't good enough for the rest of the web, and thus we had the WebP format being born. Now, the WebP format is new. It's not necessarily supported by all browsers as of this date, but it's actually got some exciting properties that are really making people on the web stand up and take notice. So first off, if you compress this image with WebP, it actually drops to about 198K. That's 100 kilobytes of data difference for this single image. In addition to that, WebP will actually allow you to get transparency and even supports some forms of animation, which means this single image format gets you the compression sizes of JPEG, the transparency properties of PNG, as well as the animation properties of GIFs. It's an exciting one-stop solution for a lot of your image needs. Now, this is the important thing to note about this image size and about this image format, is that most mobile phones right now are actually about 5 megapixels for their cameras, which means people are taking snapshots of the food they eat or signs on the street or their kids, uploading them up to their favorite social media network, and that's actually coming in at 5 megapixels uncompressed. Now, if we look at PNG and JPEG and the compression ratios they got with a single megabyte image, you can see that over time, as the number of images that fill the internet increases, we're going to quickly run into compression and data size issues. That's why WebP shows up, and it actually solves a huge problem for us and allows us to address a lot of issues. Now, there's a whole separate series of GDLs done on WebP. I encourage you to go to the GDL website, take a look at some of these talks for more information on how to get started with that. Now, that's all I'm going to say about image compression for now. But in the meantime, let's talk about text, right? So I said before that text data, CSS, HTML, JavaScript, actually drive the rendering performance and initial page load of your page more than images do. This is for a very specific reason. So if you look at this graph here, we actually can't start rendering anything on your page until the HTML has been parsed and subsequent JavaScript and CSS may be loaded to create both the DOM and the CSS DOM so that we can actually parse the render tree and actually start getting pixels on the screen. So if we look at this average flow of events from HTML to CSS to actually getting pixels there, we can actually see an interesting example. So we have a standard HTML which actually links to a CSS. That CSS is updating some of the information on the page, the text data. We also have an image that's referenced and a script that's at the bottom of it. Now you can see on the mobile image on the side there that nothing has been shown yet, even though this HTML has been parsed. And so we've got our little HTML box that's mostly orange. You can see that the DOM has mostly been parsed, it's partially orange, and that the CSS file, example.css, has been discovered, but it hasn't really been loaded yet, right? So this means that we actually cannot display text on the screen because we don't have the styling properties that define that text on the screen. It's not until the CSS data actually gets loaded that we can build the CSS version of the DOM and actually begin constructing the render tree. Now notice that the DOM still hasn't finished loading yet. That's okay. If we can actually partially load and partially display the top part of the DOM, or what people typically say is above the fold, that allows us to actually start rendering pixels on the screen while the bottom part of the page is still loading. So now that CSS is loaded, we can actually get some text on the screen. Now notice that Layout and Paint are kind of halfway through their process because they don't have all the data. Loading up next should be WebP, and then of course last.js is defined there as well. Now, because of the file sizes, last.js is smaller than the image, and so it can actually get loaded and parsed before the image data actually gets to the screen. Now, if last.js kicks off some style chains or some other information that needs to be loaded, it can go back and change the DOM and change the CSS properties, forcing page reflows, forcing page repaints, and other sorts of chaos in your loading time. But notice the image still hasn't been loaded yet and hasn't been displayed on screen. It's not until the final complete bits come off the wire, the CSS DOM can be finished, the render tree can actually be completed, and finally we can actually get the image on the screen showing you what we're trying to show you in the first place. Now what you should gather from this is that while images make up the bulk of the content on the web, it's really the textual-based data that drives how and when pixels get to your screen. And when you're trying to optimize for fast path and critical path rendering on mobile devices, it's really the text data you need to get off the wire as fast as possible. Now, a lot of you kids out there are talking about some really cool internet technology called Emscripten. Now, this is a library that has been developed open source that allows developers to take existing C and C++ code and transcompile that to JavaScript data. Probably one of the most impressive examples of this technology was debuted a little bit earlier this year, sometime in March at the Game Developer Conference, where NVIDIA and Mozilla and a bunch of the open source community at Emscripten actually debuted the Unreal 3 graphics engine running on top of Emscripten. Now this means that you get this rich, full graphics engine running inside of a browser. It runs inside of JavaScript, so it's spec compliant and all this other fun stuff. Now, I'm from the games industry, and I've been working with Unreal 3 for a number of years now, and one of the things Unreal has never been popular for is being small in size. And you can actually see that when we move the source code and the compiled data to the web, this problem still consists. So if you look at the loading time of this application, you can actually see that the core JavaScript file for this Emscripten-based port of Unreal is about 50 megabytes of data. 50 megabytes to bring down a JavaScript file to actually load this game. Now, to be fair, it is served compressed, which means that you actually only have to pull down 5 megabytes of data across the wire for this single JavaScript file. But still, 5 megabytes, that's 5 times larger than any of our other websites out there. And by the way, this isn't counting the 18 megabytes worth of data that has to be pulled down as well. So when you look at these trends and the more developers that are trying to move towards high-performance JavaScript execution using things like Emscripten and Asm.js, what you start seeing is a trend. The more web applications that produce source code in JavaScript that come from other languages, we'll start seeing bloated and larger JavaScript files that need to be downloaded by their clients before pixels can get on the screen and the game can be played. This trend is not going to diminish over time. This means that our text data is going to continue growing larger. As such, as a developer, it's your job to figure out how to minimize, compress, and reduce the number of bits on the wire. And so with that, let's take a look at the good old boy known as GZIP, sort of the backbone of compression on the internet today. Now, I want to take a quick side to note that compression is not the same as minimization or minification, depending on how purist you are on the term. So let's take a look at the two really quick. Minification in the web platform is the art of removing redundant information from textual data such that we can still symbolically parse and process it when we pass it off to the underlying system, right? So if you look at this example here, we've got a function that adds 2 numbers, but there seems like there's a lot of information that you don't see, right? There's line returns, there's extra spacing information, perhaps the variable names are actually too long. The process of minification actually reduces all of this to give you the least number of completely processing and valid bytes for this file representation. Again here, we can process this ahead of time and actually pass this right to the underlying systems to be processed and actually get stuff on your screen. Now, compression, on the other hand, offers something completely different. Compression is the act of modifying your data so that it has to be reconstructed before being passed to the underlying processing system. So again, if we take the minimized form of that sum function, compression will actually turn it into a bit stream of information that then has to be deflated or actually decompressed into the original form before it can actually be passed off to the underlying systems. These two technologies work as a 1-2 punch, right? So you actually have to add minification to your technology before you allow gzipping to occur in order to get the fewest bytes on the wire. Now, for the rest of this talk, we're actually going to be addressing some of the issues and pros and cons of gzip. But before we do that, I need to make sure that we understand what's going on under the hood of this algorithm. You see, gzip is a compression format that actually uses 2 interplaying technologies together. The first one is a technology known as LZ77. Now, this is a dictionary-based transform that'll actually take a given data stream and convert it into a sequence of tuples. Now, in each tuple, we actually have a position and a length value. So I know that's confusing. Let's take a look at a little example here. So we've got this string up top, which is comprised of various A, B's, and C's in some sort of random order. Well, what happens is we start parsing this string. We're going to look at each symbol individually, and we're going to do a scan backwards to find out when previously we've seen this symbol before, because then that allows us to actually encode this symbol rather as a single piece of information, but actually as a relative piece of information. The goal here in LZ77 is actually to create a lot of redundant types of tuples that we can then compress a little bit better. So let's walk through this just a little bit so you can kind of see what's going on. So if we start with the first A here and we actually parse it, well, it's the beginning of the string, so we haven't really seen anything before yet. Therefore, we actually have to output a position and length of 0, 0. It represents that we're not actually seeing any other characters, we're just looking at the A itself. Now, when we get to the second A, we start our backward scan and we find that the first A we encounter was actually one symbol ago at a length of one symbol. So this means we can actually output the tuple 1, 1. Now B, we haven't seen any B's before, so we have to output 0, 0, and C, same thing, 0, 0. But now we've reached another B. So it's going to start scanning backwards and actually finds the last B we encountered in the stream was 2 symbols ago, and again, we only want length of 1. Now the important and probably the more interesting part of this particular example is when we get to the end of the string where we see A, B, C. Now when we scan backwards from A, B, C, we can actually find that we found this exact 3-symbol value previously in our stream, and exactly about 5 character positions back. So this means we're going to output the tuple of 5, 3. So we output a tuple rather than the 3 characters themselves. Now again, the point of LZ77 is to actually create sort of duplicate and high redundancy tuples. These tuples and the redundancy that we create with them are actually very important to pass off to the next step of the GZIP algorithm known as Huffman compression. Now, for those of you who don't remember Huffman compression or probably have blocked it out of your mind back from the Computer Science 101 days at your university, Huffman works by assigning variable length bit codes to symbols in your stream based on probability. The idea here is that the more probable and more frequent a symbol is in your stream, the least bits you should use to represent it. A perfect real-world example of Huffman encoding is Morse code. In the American language, the letter E is the most dominant of all our words, therefore it's assigned a single beep to represent its value. Huffman compression works a similar way. Now we're going to spare you the knowledge of building a Huffman tree and everything else. This is in tons of data structures books. Instead, we'll just show you that we can see as we parse our newly tokenized tuple string, you can see that 0, 0 is the most dominant tuple set. And of course, we can assign that 1 bit being a single 0. Therefore, the next set is actually 1, 1. We have 2 symbols of that, and because of the way our tree is constructed, we actually have to provide that with 2-bit symbols. We continue on and effectively keep assigning variable bit code words to symbols, creating a compressed version of our data. Now, these 2 characters, or these 2 algorithms operating back and forth with each other, actually have a very beautiful ballet in the way that content is created and how it's compressed with the statistical encoding. This is the cornerstone of everything we're going to talk about for the rest of this conversation. Now, it's worth pointing out that GZIP is not the only kid on the block. In fact, GZIP is about 20-something years old now. I mean, if it were a real human being, it'd be able to drink and drive and do all other sorts of fun stuff on the internet. But other compression algorithms, which may be a little bit newer and a little bit different, can actually give you some interesting trade-offs. So here are 4 of the more popular encoders out there. The first is one known as LZMA. Some of you may know this more popularly as 7-zip, a very popular compression archive tool out there. You can see that LZMA actually gives you smaller compression than GZIP. This is actually due to a lot of higher order searching and finding algorithms built around that LZ77 algorithm. In fact, LZMA can actually be considered a distant cousin to GZIP because it's actually very similar in the way that it compresses its data. However, because it uses more modern heuristics and algorithms, it can actually get better results. Now, below LZMA, you see LPAC. This is a context mixing-based encoder. It's effectively mostly a neural net in practice of how it matches symbols. Now, notice LPAC actually gives us the smallest file size compared to everything else at 0.35 megabytes. I'll get into that a little bit more in a second. Now, the final compressor we look at is actually BZIP2. Now, BZIP is a modern variant of the Burroughs-Wheeler transform, assigned also with a move to front transform and either a Huffman or an arithmetic encoder on the back end. Now, BZIP2 fundamentally changes the way that compression works. It's very different. It doesn't use LZ77 at all. Instead, it uses a semi-block-based sorting transform to actually increase redundancy or adjacent redundancy in data. This redundancy allows it to get better compression. And again, you can see here where GZIP actually gives us 0.48 in terms of megabytes, BZIP actually beats this. Now, what you're actually seeing here in terms of data sizes is actually a scrape I did of the Amazon.com homepage. So if I take all of the text data from that, HTML, CSS, JSON, and JS data, it actually comes out to about 1.64 megs. So you can see how these compressors relate to that specific memory footprint. Now, when you're comparing compressors, the size of the data is not the only heuristic. You have two other heuristics that you typically throw into the mix. The first one is encoding time, and the second one is decoding time, which often is the more important of the two. So if we look at the encoding time column, you can see that GZIP does probably the fastest in terms of encoding speed at 0.79 seconds. LZMA, being a distant cousin with more search heuristics, actually comes in pretty close at 1.26. You can see that the wins it gets from in compression size actually come from more pre-processing at the front of the encoding step. Now, LPAC gives you amazing compression, but notice it actually takes about 11 seconds to compress your data. Now again, LPAC is a modern wonder. It actually uses various forms of context mixing in different sort of combinations, again, resulting in pretty much an artificial intelligence neural net algorithm to find compression wins. So it makes sense that this actually oscillates at about 11 seconds worth of processing time because there's a lot of things going on under the hood. Meanwhile, the Burroughs-Wheeler transform-powered BZIP2 doesn't stray too far from the mark, but gives us about 2.1 seconds in encoding time. And there's a whole set of papers that talk about how that clustering transform actually affects memory and processing and whatnot. Now, decoding time is probably the most important part here. You can actually see that GZIP and LZMA are, for all practical purposes, identical, right? So while LZMA takes a little bit longer to encode, it seems to regularly produce smaller files than GZIP, and the decoding time tends to be almost identical. Now, LPAC, again, because it's running a neural net, the decode time actually equals almost what the encode time was, so you look at about 11 seconds there, while BZIP actually is a faster decode than it is an encode. The whole point of this slide, the only thing I want you to take away from here, is that GZIP is really good at a couple things, specifically encoding time. It gets beat in a couple places, specifically with the size of the compression that it achieves, and then ties in a couple other places in decoding time. So it's not really the only algorithm on the block there in terms of compression ratios. So you can see here that we've highlighted a couple of these specific instances, right? LPAC wins in size. Encoding time is, of course, dominated by GZIP, and decoding time is, of course, dominated by LZMA. Now, this can lead a lot of people on the web tech platform to actually come at me with burning pitchforks and actually say, hey, GZIP is actually pretty good. That data just showed us that we really don't need any other compression algorithms because it gives us decent size compression, decent time for encoding, and decent decoding time. Well, I'm here to tell you that's a good argument, but let's dig a little bit deeper into whether or not GZIP should be the only thing we allow on the web. So first off, you should understand that there's really no silver bullet for compression. Depending on what your data is, how frequent it is, the relationships it has with local information, all relate to how well it can be compressed at the end. And different compressors will handle this data in different ways. For example, if you actually applied JPEG-style compression to text data, you're not going to be able to decompress your text in the right way because it's lossy in terms of removing information bits from the stream itself. So let's take a perfect example that actually shows to beat GZIP without really any modification. So let's say we have a string of integers here. Now, this string of integers was actually created as an index system into some higher order database, right? So there's basically 10 things that are being indexed, and we list them here. Now, if we just gzip this, we actually don't get a lot of savings. This is because if you remember the LZ77 algorithm, isn't going to find any duplicate indexes in this array, right? 9 is only existing once, and so are the other numbers. Meanwhile, that means that all of the statistical probability for these symbols is pretty much equal. There's no difference. Nothing is more frequent or less frequent, which means the Huffman algorithm is going to pretty much assign equal bit lengths to all the symbols themselves. Because of this, we really don't get any compression savings at all from the GZIP algorithm for this particular data stream. This means that, you kind of have to look at your data and go, what is GZIP doing to it? If we, however, take a little bit different swing at the problem itself, we can actually beat what GZIP is doing with a little knowledge of our data. So let's say we take the original array, And instead of just leaving it by itself, we actually notice the property that we can actually sort this information because we don't need the order to come out on the backside. So if we sort this, we actually end up with a pretty incrementing run of numbers, 0 to 9 without any gaps in the middle. We can apply this, we can take this string and apply a technique known as delta encoding to actually create a different symbol set. Now, delta encoding works by taking a symbol and finding the difference in the symbol between the previous symbol, and it encodes the difference rather than the actual value. So for our specific example here, we start with the number 0, and the number 1 is 1 more, so we add 1 to that. 2 is greater than 1 by a single value, so we add 1, 1, 1, 1, 1, 1. And you can see with delta encoding, all we have to do is encode 1 and then 8 zeros to actually represent the original string we have. Now, the delta encoded version, notice that it does have a lot of duplicate symbols, and there is a particular symbol which is more dominant than the other symbols. Now, once we've encoded our form into this, once we've encoded our data into this form, GZIP actually has a field day, right? The LZ77 algorithm finds lots of matches in its window, and the arithmetic compressor can actually come through and assign smaller bit codes to more frequent streams. What we're showing you here is that you can't just throw arbitrary data at GZIP and expect to get the most perfect, amazing form of compression. Instead, a little bit of pre-processing can actually change the way your compression works, most of the times for the better. Now, let's look at another perfect example of where GZIP can actually cause some problems. So if you look at my website, I did a little bit of an analysis a while ago on various forms of CSS minimization technologies. There's a fantastic set of code out there by someone who is using genetic algorithms to figure out optimal ways to minify CSS data. So let's take a look at this table here. So if we take two CSS files from Stack Overflow and Bootstrap, and we actually look at their minified form, so this has already been run through Clojure or YUI or Clean CSS, one of these things, we actually get about 90 and 97K respectively. Now, using the genetic algorithm version of the minifier actually produced about 3% savings in both of these files, which meant that we can use a different variant of minification to get wins over what we're typically already doing. So this is a good idea, right? If we find a better algorithm that minifies our data smaller, we should be embracing that. This is where GZIP actually causes some trouble. When we actually run these genetically, algorithmically minimized data through the GZIP compressor, you can see the results are actually negative. That means that it's actually growing the data, right? So we have our minified.gzip, right? So if we just zip the data that comes from Clean CSS or Clojure, we get about 18 and 15K. However, when we zip the data that's been generated from our genetic algorithm, you can see that we're actually increasing the size of the file. Basically, what you're seeing is that the data is so minimized coming from the genetic algorithm that GZIP is actually inflating the data. It's making your file larger than it should be because it's only using the LZ77 and Huffman encoding steps. Now, this should scare a lot of people, hopefully, into thinking how often this is actually occurring on the internet for various sizes of files. Now, I can tell you it's not that frequent, but it is something to keep an eye on because it definitely shows that GZIP is not a silver bullet, and it can actually do harmful things in very certain circumstances. Now, of course, a lot of people here would then say, well, you know, this means we shouldn't be using this genetic algorithm to minimize our CSS. Obviously, that's a flop, and I still think that that's the wrong argument, but let's move on. Now, let's talk about PNG for a minute. Now, PNG is a format that you can actually export in a compressed form. Now, internal to PNG, the compression algorithm it uses is called deflate, pretty much the backbone of what GZIP uses. It's an LZ77 coupled with a Huffman compressor step. Now, what you're looking on the screen here is two images. Effectively, I took a 90 pixel by 90 pixel sprite and I tiled it vertically, creating a 90 by 270 image. Now, I also made I resized that image just a little bit and add 2 columns of pixels. So we now have a 92 by 270 image instead of a 90 by 270, right? So we've barely altered the size of the data. However, you can see at the bottom there that the sizes post-deflate, post-GZIP, are drastically different. The 90 by 270 image is about 20K, while the 92 pixel image is 41K. That's twice as large for only 2 columns of pixels being added to the image. And again, the compression algorithm that's being used under the hood here is effectively GZIP. So let's take a look at why this is occurring and what's going on. So let's say we've got a bunch of pixel colors here, right? Well, remember the LZ77 algorithm is going to come through and it's going to try to find matches. So we've got a particular green pixel here and another green pixel that's identical to this somewhere previous in our data stream. Now, how this works is that LZ77 won't scan infinitely to try to find matches. Instead, it actually operates in a window of 32K worth of information. Now, that means if I encounter a symbol that's outside of that window, then I'm not going to find a match. It only matches things inside of 32K window. So if we look at our 90 by 90 images that we created for our tile sheet there, 90 times 90 times 4 bytes per pixel is roughly about 32K in size. Now, if we actually look at 32 times 1024, the real definition of 32K, it's again, about 300 bytes larger than our 90 by 90. However, when we added those two columns of pixels, we actually changed the size and the stride of our images. 90 by 92 by 4 is actually 33K, not 32K. What this means is that when we're trying to find duplicate pixels in this image, we're just far enough away that we can't find the exact pixel that we had seen before. Let's take a look at this visually. So again, we have our two images, the 20K and the 41K, and we can actually create a heat map for this image representation. Now, this heat map shows us in dark blue pixels being the ones that are highly compressed. This is where matches have been found. They're very small encoded pixels at this point. Meanwhile, reds and yellows mean that we didn't find a match, and to encode this particular pixel took a lot more bits. So you can see on the left-hand side, where we're 90 by 270, we actually get a lot more matches. The dominant form of the image is dark blue, right? You can see once we tiled that image in the lower two regions that we find an exact pixel matching 32K pixels away. However, when we increase the size by two columns, we've actually bumped out the window of pixels to look at. Therefore, we're not actually finding exact matches. In fact, we have to look for near matches, and that's why the second image has a lot more misses in the LZ77 cache, resulting in worse encoding. Now, this basically shows us that with small changes to our image data, the GZIP algorithm actually falls completely on its face. Again, it's far from being a silver bullet. Now, the truth is that at this time you should be saying, well, hey, it'd be great if we could use one of the newer algorithms, but in reality, we're stuck with GZIP for some indefinite future. Here's why. If you actually go with the Chromium source code and look at the bug system that's provided there, you'll find an interesting tale of how Chrome actually adopted the bzip2 compression format. Effectively, Chrome added support for it, and a lot of servers, Apache and whatnot, added support to send out bzip2 content. So effectively, a server creates a bzip2 file instead of gzip and sends it off to servers. However, what started happening in the wild was a little bit interesting to us, and the results made us actually have to remove the support for bzip2 from Chrome. You see, what was happening was a lot of these middle boxes that are out there in the wild didn't ever expect that we would do anything besides gzip. And they actually had hard-coded paths in there to look and say, if this is not gzip header compressed, compress it with gzip. So effectively what occurred was some servers would receive the bzip2 archive with a bzip2 header, and these middle boxes would look at it and say, hey, this isn't gzip, strip the header, try to gzip the information, and then send it out. This means Chrome would actually receive a bzip2 data package whose header had been stripped and then it had been re-gzipped. So we would have no idea what the actual format of the data is that we're receiving, right? It could be binary data or it could actually be valid information. The problem was this was so systemic out there in the wild for various types of firmware and middle boxes that it was actually too difficult for us to fix on the fly, which means it was a smarter idea to actually just remove this from Chrome. So when you start talking about the ability to add other compression algorithms to the base browser, you're going to run into the same problem, is that there's a lot of systems out there who just don't understand and haven't been updated to expand to different sorts of compression technologies. So this gets us to an interesting idea of, well, if we're kind of stuck with gzip, but size of text data is a problem, how do we actually create smaller gzip files? Well, lucky for you, I've actually spent the past 3 or 4 months focusing explicitly on this problem. And you can actually see a lot of the results on my blog at mainroach.blogspot.com. But first, let's dive into a couple of these ideas, and then you can go there and read about all the awesome things. So first off, we can actually generate better gzip files. A lot of people don't understand this, but when your server creates your gzip file, a lot of them are only tuned to compress it at a factor of 6. Now, the gzip command line option allows compression ratios, or the command line parameter that you pass to gzip allows you to pass in between 0 and 9, where most of the servers are default set to 6. This seems to be an interesting trade-off between compression speed and compression size. Now, this is mostly because web developers tend to just upload raw assets to the server, not wanting to deal with compression. The server actually is responsible for compressing the content and then sending it off to requests. Now, what's interesting about this, though, is that you can modify your files and actually gzip them offline. So effectively, you would actually, part of your build step would be to take your text information, gzip it with some better compressor to produce a smaller gzip file, and then actually tell the server to just pass that data through. There's two applications out there that can actually produce this type of smaller gzip file. The first one is 7-zip, right? This is actually a very nice command line tool which can produce bzip2 archives as well as gzip archives, but it does so taking advantage of the more modern, more powerful searching and dictionary-based compression algorithms that it's going to be using. So 7-zip can actually produce smaller versions of gzip files than the standard command line gzip archiver that ships with most firmware in servers. Another fantastic tool out there is one called Zoffly. Now, this was actually created by the engineers here at Google to solve this same problem. Now, Zoffly uses a lot more memory and a lot more advanced algorithms than even 7-zip to find better matches in smaller spaces to produce smaller gzip files as well. It's an open source project. You can go check it out. I highly recommend it if you're interested. So the cool thing is we can use either 7-zip or Zoffly as part of your build process to actually generate smaller text files and have them sent along on behalf of the user. And again, these are gzips, so they're going to be accepted by the middle boxes as well as the browsers. Now, if you're wondering how these pre-processing systems actually fare against the standard gzip, here's a great graph to look at. So you can actually see the blue column across a bunch of files is actually the standard gzip algorithm. The red one is actually Zoffly, and the green one is actually 7-zip. So you can see across these 42 files that on average, in fact, most of the time, both Zoffly and 7-zip regularly beat gzip by somewhere between 2 to 10%. And if you actually increase your parameters and allow Zoffly and 7-zip to spend more time doing matching and doing compression, you can actually get it into the 15% ratio, which is fantastic. Now, the cost of this, though, is enormous, right? A lot of these algorithms took probably 20 minutes to run on the light side to find 1 to 5% worth of compression wins. Basically, what we found is that we're at a local minima for compression. The more time we spend trying to compress the content yields less and less and less actual savings. You can spend 6 hours of cloud compute time to get 2% savings in your compression algorithm. So at this point, you kind of have to look and say, well, if we're stuck with gzip, yet it takes additional hours of time to compute smaller gzip files, what the heck is this entire talk about? Aren't we just kind of stuck in this? Fret not, my good friends. You're actually not stuck, and it actually comes down to you owning your data. You see, you can create smaller gzip files by actually pre-processing your information before handing it off to gzip, much like the example I gave earlier where we took a set of numbers and then delta compressed them to create something that was highly repetitive and highly compressible. You can apply these techniques to a lot of other portions of your code base. So let's dive into some interesting algorithms you can use in your projects today. The first one happens to be close and near to my heart. Now, many applications and many websites out there use JSON as a format to transfer data between client and server. Social media information is typically sent around in this information. It's a very nice, very adopted file format for sending information around, particularly because it's built off the JavaScript standard. Now, when you're sending this data around, though, most of the time users and developers don't think about how to modify the data being sent such that it compresses better, right? So the user asks for some search query, the server goes and computes the information and then returns the JSON blob back, normally optimizing for return round trip time, right? It's trying to get the data back to the user as fast as possible. But what they don't understand that if they actually have that gzip flag turned on, gzip's going to stop the operation and zip the content before sending it down to the client anyway. Now, if you're the type of developer that's dealing in third world countries or other types of connectivity that may be sparse sparse or intermittent, this is actually a huge problem, right? Because your client device, usually a mobile device on some 1G or 2G network that may or may not stay consistent, is sending off requests, and then what's hurting them is that they're getting a larger payload coming down. So basically what we're talking about now is how can you process your JSON blobs that are being returned to these individuals in such a way that GZIP can compress it further. And it all starts with the ability to transpose your structured data in your JSON file. So let's take a look at this example. Now, I've scraped a lot of websites and a lot of JSON responses, and I see this pattern occur on a lot of websites. Effectively, what you're looking at is a list of dictionary structures of name-value pairs, right? So someone requests a search for a particular item on a shopping website. It's very common to actually return to them a dictionary item that actually contains, what the product name is, what the price is, what thumbnail image to use, etc., and then just list these linearly inside of an array. So what this creates, though, is an interesting problem, is that similar-based data is actually strided away from each other. It's actually interleaved, right? So you may have a name and then a price, which could be a floating point value, and then a description, which may be a long form block of text, and then a URL, which has its own specific characteristics. What we're proposing in transposing our data is actually turning this name value pair and actually de-interleaving it, and instead actually grouping similar values for property names together. So example here is we have these two dictionary objects that both have name and position values, and instead we can transpose that such that we have an array of name answers and an array of pose answers, right? Now, I know this looks weird at JSON, so let's take a graphical look at things. So let's say on the top here we have an array where we have a list of objects, and each one of the colored blocks represents a property on that object, right? So we've got green is a name, and blue may be a price point, and again, red might be some URL. What we can do then is we can actually transpose this and align all of the green blocks, blue blocks, and red blocks together, allowing the data to be, allowing homogeneous data to reside in an array with other homogeneous data. Now, I'm going to explain why this is actually an improvement in a second, but let's see if we can take a look at whether or not this saves us any data. So if we take a bunch of JSON files that are returned from very common websites, so I took some responses from Amazon and Pinterest and whatnot, you can see that the first column represents the source size in bytes, the second column represents the source data actually gzipped. The third is actually the size of the data after it's been transposed. You can see that there's some variability in numbers there because we're actually removing symbols from the string at this point. And you can see the final column is actually the gzipped version of the transposed data. Now, we're actually in an interesting situation here, is that for some JSON files, the gzipped form, the transposed gzip data is actually smaller than this source gzip data, which means we actually get a win by applying this process. Thankfully, we're not falling into that area where genetic algorithm minimized CSS is actually causing gzip to inflate the data, right? We don't want to be there. So the transpose operation actually gives us smaller files, which is fantastic. Now, the reason that this actually works has to do with the 32K window that LZ77 uses for its matching, right? So if we have our values here that are all interleaved, right? Red, green, blue, red, green, blue, red, green, blue. Again, we have to go farther to search for a piece of content that may be an exact match. However, when we transpose our data, we de-interleave it and group similar types of data together. So let's say we're actually trying to find a match for one of these green values. In the top array, you can see that an entire listing of data, the green may not fit inside the 32K window. Meanwhile, once we transpose it and group homogeneous data together, the entirety of the green data actually fits in a single window. This is going to allow you to find better matches, which is going to result in smaller compression values. Now, this actually comes to another step here, which is like, okay, well, if we can transpose our data, how else might we modify our content so that we can get wins? Now, this is a really, really cool algorithm that I found digging through the archives of IEEE, known as compression boosting. Now, it operates on the same parameters. How do we pre-process things for better compression? So the first one we're going to take a look at here is actually something called dense codes. Now, this is some great research out of some academics in Argentina, and effectively it allows us to take a text-based file and pre-process it and hand it off to GZIP. Now, the pre-processing is actually the important part here. We're not actually transposing it, but instead we're using a modified dictionary index lookup scheme. So let's say we have, we parse our text in our scene and we create an index, a dictionary index, right? So once a word is seen, we provide it to the dictionary, and then every reference to that word is replaced with an index value to the array, right? So let's say we have array here of how much wood could a woodchuck chuck, and we have 400 symbols before that. So we see that how is at location 400, 401 is much, 402 is wood, 403 is could. So when we're creating a stream, we're going to get values that point into these element arrays, right? So the problem with this is that if we only have 256 symbols, we can only use 8 bits per pointer. However, if we go above 256, we have to start using 16 bits per pointer, which is actually a problem, because if the symbols are weighted such that the most probable and most visible symbols are actually closer to the front of the dictionary, you're actually going to be wasting a lot of space, right? You're going to have a lot of symbols and a lot of indexes where the first upper 8 bits are actually going to be zeros for the entire dominant side of it. So you're actually inflating the size of your stream at this point because there's a lot of bits that aren't being used. Now, the way that dense codes work is it actually allows you to modify the way the token is used to create the ability to actually do variable length coding in string, which means that for the first 3 numbers, we actually use 16 bits to represent the indexes, but the second 3 numbers, because their indexes are lower than 256, we can actually use 8 bits instead of 16. So this is actually going to create a smaller stream for us to actually compress a little bit later. Now the wins from this are pretty interesting to look at. Because there's a couple things in flight here, and I've got a write-up, an entire 10-page write-up on my blog about this algorithm and the interesting things that go back and forth between it, some caveats and some things you need to know, but it all boils down to this table. Now basically what this table says is that we've tried the source data being gzipped, and then we've tried the data being run through our dense codes, that's the etdc column, and then the gzipping of that information. Now, next to it, I actually compare the other compressors that we've mentioned today, right? Zoffly, 7-zip, and bzip2. So what I'm trying to see here is that once I do this pre-processing, what compression algorithm is actually going to give us the best results? You can see that hands down, GZIP really doesn't produce savings with this pre-processing method for the majority of the data that I've shown here, right? JSON files, CSSs. And I've actually run this probably against 25,000, 30,000 files, and you see this similar pattern, that just doing standard GZIP against this information doesn't really give you a wins. However, you see when you start using Zoffly, you start getting some wins, right? The advanced pattern matching and more memory usage characteristics that it has inside of an encoder allows you to get better matches with this, producing smaller files. The clear winner here is 7-zip. Something inside of the way it's using its algorithms consistently produces smaller, dense code compressed files as opposed to the source data, which means this is interesting that if you have data that's above a certain size, let's say you're returning a 20K blob of data for some reason, pre-processing that text with dense codes and then using 7-zip as your compression algorithm of choice can actually produce, or your compressor of choice can actually produce smaller gzip files consistently. Now the downside of this, of course, is that you had to reconstruct your dense code transform at the client, but that's not necessarily a big deal depending on what type of trade-off you're willing to make. Now these are all pre-processing schemes. There's another form of processing your data that can actually get wins that these can't touch. I mean, the types of wins that we're going to talk about for Delta.js blow these pre-processing schemes out of the water, but be warned, there be dragons here, mostly in the form of madness. So let's dive into what I'm talking about here. So in 2012, the Gmail team actually did a fantastic presentation for the W3C and actually put up some slides that are publicly available to other information that was proposing a solution to a common problem. You see, Gmail users see about 61 years of loading bar inside of Gmail about every day, right? This is a lot of time that users are seeing just sitting around waiting for JavaScript to be streamed out. What they proposed was a new form of ability to, instead of transferring the large files every single time, they can actually start transferring the difference between the file that the user has and the new file that the user needs. Now, this isn't a new concept. We've seen these sorts of patching-based systems everywhere in computing since the late 1970s, but it's never been able to be applied to the web due to some of the architecture involved. How the algorithm works is this. So let's say we have a file.css version 0, and we've made an update to it, right? This happens quite a bit in large projects. Now, when we make that update, the majority of the file is the same as it used to be, right? There may be a function that's added or some comments were placed in or some things were removed, but for the majority of the file, it's almost identical, which means we can represent the second file, the new file, as a difference from the file that we've already seen, right? This is the concept, again, of delta encoding. Now, once we've delta encoded this file, the patch, basically the difference between the two, is generally much, much smaller than the updated version of the file, right? Which means we can represent version 1 as a patch operation of version 0, right? This means that if the user already has version 1 on their machine, all we have to do is send them the patch, and it allows them to reconstruct and create the new version of data. Now, this is actually a pretty interesting concept because this means we don't have to send full files to the clients all the time. Instead, we can produce and send down highly, highly minimized content to these guys. Now, of course, this comes with a bit of overhead in terms of communication, right? You see, in order to get this working, we have to have a communication process between the client and the server. So let's say we have our mobile device here and the user is going to load a website. Well, the client actually needs to notify the server on what version of the file it has cached. The server can then take this information, look up it in its array, and figure out what patch file it needs to send to the client in order to get them up to date. Once it's figured this out, it passes it off to the client, and then the client is going to use this patch to construct the new version of the file and cache that and use that appropriately. Effectively, this technique is trading network requests for smaller file sizes, right? Sending a couple byte request to determine what version of the file you have is going to be night and day difference than actually doing the entire file being sent to the user multiple times. Now, if this sounds like craziness to you, just hold on. You have to realize this is a common problem for many large, very industrial websites that serve millions of users a day. You see, when the Gmail people actually looked at what the type of savings they can get from this type of algorithm, they saw a massive potential for improvement here. You see, when they compared the number of revs they do to a single file over a month against the sizes of the deltas if they were using this scheme, they actually saw that a whole month's worth of changes was about 9%, lower than 9% of the size of the assets altogether, which means they would only have to send 9% of the content as opposed to the new full file each time. This is a huge win. We're not talking about 10% improvement. We're not talking about 50% improvement. This is 90% size decrease by using this delta algorithm. So obviously this was a proposal to the W3C spec. I've talked with some of the Gmail guys. It doesn't look like this is actually live in the servers right now. If that's changed, I hope to be wrong because this is a fantastic piece of technology that I hope to see rolling out in some form to a lot of other distributors on the internet. Now, there's another form of this compression that I've actually been playing around with. It actually comes in the form of horizontal compression. Typically, when we think of delta encoding for files, we think in terms of patches, right? I've got version A and version B, and I want to generate the patch between the two. This is especially common in game development. However, there exists a form called horizontal. And how this works is, let's say we have a cascade of files that may be similar on a website, right? So this particular website uses 3 CSS files, right? Let's say it's Bootstrap or something like that, right? Well, the interesting thing is that these CSS files generally aren't that different from each other. There's actually a lot of shared syntax on a website for a given CSS file, which means that instead of doing delta compression between versions of the file, we can actually do delta compression between the files that are going to be sent to the user, right? So we can actually do a difference between file 0 and file 1, and then file 1 and file 2. This actually allows us to create patches for each one of these, and when we combine that with the source file to your server, the size of the assets that need to be sent down to the client is drastically reduced. We can actually send them the entire application and all the content required as deltas from base files. This, again, is just an extrapolation of various forms of delta algorithms that are already used out in the wild. Now, how this works on the client side is that the server will, of course, provide to the client the base file and then the set of patches, and then the client is responsible for reconstructing each one of those files and then caching them locally. This is a really neat idea if you're trying to optimize first time load for users, right? The Gmail proposed specification requires that the user have to download version 0 of the file, which in some cases actually could be 300K of CSS data, right? Meanwhile, horizontal compression suggests that it may not have to do that. It may only have to send down bytes or chunks of 50K data when you actually represent that CSS as a delta. Effectively, what you're doing in this horizontal scheme is you're trading client-side processing for smaller transfer sizes. This is because it actually takes a lot of CPU cycles on the client to reconstruct these files before passing them off to the processing system to create your DOM and everything else. So there's this interesting trade-off between sort of delta.js or vertical delta encoding for files and the horizontal delta encoding for files as well. Now we can see when I've applied this technique to some various sites on the internet that we actually get some interesting numbers out of it. So I took all of the CSS from a Gmail session, all of the JavaScript from a Gmail session, and all the CSS from an Amazon session, and I ran it through this technique. So you can see we've got the source, the GZIP source, and then the size of the data once it's been delta encoded, and then of course the GZIPing of the delta encoded data, right? Because we can't just stop at the delta encoding. So you can see for Gmail, we actually get some pretty amazing savings. 31% and 12% by using this horizontal delta compression encoding. Meanwhile, something weird's going on with the Amazon data where we actually get an increase of size by 13%. Now, I'd like to actually point out that this data is highly minimized and highly redundant, right? All of these files that are creating multiple network requests tend to be self-similar, and that's actually due to the minification processes that are being applied to these files on the web. To give you an example of how important minimization is to horizontal delta compression, let's take a look at the game library known as Impact.js. I love this library. It's fantastic. If you're a game developer and you're looking to make HTML5 games, definitely give Impact.js a look. Effectively, I took the source file and actually combined it so it's one large file. I left them as loose files. I did not combine them into a single large file. I actually created the delta between all of these files and then did the gzipped version of that. Now you can see that it actually goes down from about 70K to 21K. However, when I minimized all of the files before doing delta compression, I actually got a better savings, right? I got down to about 14K. This is because the minimization techniques that we're using on the web today actually produce a lot of duplicate symbols that can be used in various places, right? Again, when you see those original examples of taking sum, right, and we rename the parameters that are being passed to it as ABC, we tend to see that pattern occur for all of the JavaScript for every function that's been defined, meaning we're going to see more matches result in better statistical probability, which results in smaller file sizes. So by minimizing our data before we do our delta compression, we actually get very important wins. So what we've kind of talked about today is where GZIP sits on the web platform, right? We've got a lot of text data that's about to blow up. We've got mobile devices, we've got fragmented hardware, we've got different connectivity all over the world, but some things here allow you to take advantage and actually address these issues today rather than waiting for network times to increase. So for example, we looked at the fact that GZIP is not a silver bullet. By pre-processing your data, you can actually get some pretty big wins. We've seen where GZIP actually falls on its face. If you've done a lot of pre-processing, it may not compress your data, and in fact, it might inflate it. Or if in the case of PNGs, modifying the window matching by slight parameters can actually upset how well GZIP attaches to your data. We also looked at how to pre-process your content using various forms of other command line algorithms like Zoffly or 7-zip, and then how to transpose your JSON data, which is fantastic for a lot of you shopping sites. Also, when you combine that with the dense code boosting, which is more sort of cutting edge text pre-processing data, you start getting a sense that the web is not done yet. You're not locked into your form that you have. Then you can start looking at the delta compression methods and start looking at the ways to actually combine your data in different ways to reduce duplication and complexity in the content that you have. And when you apply all this together, you start getting a vision of the web that we can actually control more of our data to reduce the sizes and actually get around a lot of the hitches and problems that GZIP present to us. So with that, thank you for your time today. I really appreciate you listening to this ramble on some very hard compression stuff. If you're interested in more, I highly recommend you check out html5rocks.com. I recently put up 2 articles there on text compression for web developers as well as image compression for web developers, and these are generally meant to be opener tutorials to introduce you to different terminology and different algorithms and how they're being used. Once again, definitely check out the Perf Matters hashtag. A lot of smart people are there, and join the Google Plus Web Performance community. You can actually see the short link there on the side as goo.gul/webperf. Again, a great place to talk about performance problems and find issues. That's it for me. My name is Colt McCandless. Here's how you get a hold of me for email and other various social media times. Thanks once again for tuning in to this episode of Google Developers Live. I hope to see you again soon. Thanks.